All right, so in this lesson, I'm going to be going over the idea of a sampling distribution. Sampling distribution. So what is a sampling distribution? Well, a good way to start is just to think about what we do in the real world. Like, let's say we're trying to answer some question. Let's say like we're trying to figure out what proportion of people prefer cats over dogs. Now we all know that's it's going to be very low, obviously, um, but we can't realistically ask every single person whether they prefer cats or dogs. In the U.S. alone, it would be 300 plus people. I'm sorry, 300 million plus people actually, and that would not be realistic to do. So we take a sample, we ask a group of people, maybe let's say we ask 1,000 people the question, do you prefer cats or dogs? And then let's say out of those 1,000 people, 21 answer that they prefer cats. And so then that 21 over the 1,000 would be our statistic. That statistic, 2.1% roughly, is going to be our statistic that we're going to use to estimate what the true proportion of people for cats over dogs would be. The true proportion of people is known as our parameter. So the parameter is the true value of what we're trying to figure out. The statistic is basically the value that we get from a sample. Now, you could also, apply this if you're trying to the mean of something. Maybe you're trying to figure out, what's the mean amount of money that someone spends eating out every week. So again, you can't ask every single person. So you ask a sample of people, maybe like again 1,000, and they tell you, I spend $50 a week. So then that $50, you get that mean of 50 from that group of 1,000. That would again be your statistic. And we're going to use that statistic to estimate what the true mean of the population is. The true mean of the population is the parameter. Our estimate that we get from our sample is our statistic. Now, probably up to like this point in your stats class, you've probably seen like X, R, and then mu, and then P and P hats. So now we're really going to go into like how we use them. So when we're talking about the true value of a parameter, if it's mean, we're going to use mu for the population mean. And if it's proportion, we're going to use P, true population proportion. Now, when we're talking about samples, to represent the sample mean, we're going to use X bar. And to represent sample proportion, we're going to use P hat. So this is a way of letting us know, like, hey, we got this proportion from a sample. You got this mean from a sample. Or we got this proportion from the population. Or we got this mean from the population. Now, those are actually a big deal, especially on your AP exams, and make sure you use these correctly. The readers I know are pretty strict when they grade your free response on that. All right, so let's go ahead, let's do a practice problem. All right, let's look at this practice problem. So here we have a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and then calculates the 75th percentile and the sample is 56 inches. So think, what would be the population? What would be the parameter? And then what would be the sample and the statistic? All right, and the answer is going to be something like this. You should be able to say that the population are all the 10-year-old boys. That's the group that the pediatrician wants to understand. That's the group they're studying. The true value is the parameter. So the true value of the 75th percentile is the actual, value in the population of all 10-year-old boys. The sample, though, that she uses to estimate this is those 50 patients. And then she gets the statistic from the sample, which will be 56 inches. Now let's look at the second one. So the Pew Research Center poll asked 1,102 12 to 17-year-old boys in the U.S. to have a cell phone. Of the respondents, 71% said yes. All right, so our population would then be all the 12 to 17-year-olds in the U.S. That's the group they want to study, and the value that we're trying to figure out is the true proportion P of 12 to 17-year-olds that have cell phones in the U.S. Now, again, they did this study, and they found out of those 1,102 people that they asked, which is our sample, that they got sample statistics, so they got p hat to be 0.71, 71% of them said yes. Okay, so that's the first thing you need to know before you can really understand what a sampling distribution is. Now let's talk a little bit about how a sampling distribution works. So going back to those problems, let's say going back to the hypothetical question where we were trying to figure out what proportion of people prefer cats over dogs. So we asked 1,000 people, 21 of them said they prefer cats over dogs. Now we have to think, if you were to ask another group of 1,000 people, are you going to get 21 again? Probably not. You may get something around 21, maybe you get like 18, or maybe you get like 30. But you're probably not going to get 21 again if you ask another 1,000 people. Now, do this again, ask another 1,000 people, you get the same number. Let's say you get 21 and then 30. You're probably not going to get 21 or 30 again. You get like 25. So the idea is that when you ask different groups of 1,000 people the same question, you're probably going to get a different value for that statistic. And all of these statistics make up a sampling distribution for a specific size of sample for whatever we're trying to figure out. So let's do an example so this can make more real sense. So an activity that I'll do in my class is I'll have a bag of 200 colored chips, and then 100 of them, actually have the same color. 100 of the 200 are red, so 50% of them are red. So our population proportion is 0.5. Now, what about if students had to try to guess what it was? So let's say they didn't know, and they had to guess what the true proportion was, and they could only take samples of 20. So I basically pass around the bag. They pick out 20 chips, and then they count how many of them are red. Let's say they get 11, and then they use that to 11 out of 20 to give a sample proportion for their estimate of the proportion. So the idea is that I'll do this, multiple times with groups of students. I try to do at least 25, 30, and then we try to see what actually happens. Like, what proportion are the students getting? How does this actually work? And how does this actually work? Like, are we actually going to get values close to 0.5, or are they going to be all over the place? So the last time I did this with I think I did it with about 35 students. And let's turn to the next page so I can show you exactly what happens. What I would do is have them record. We all record our data. So let's say the first group, maybe gets 11 out of 20. And so then their p hat is actually 0.55. So let's say p hat is 0.55. And so let's say the next group goes, and then they get 12 out of 20. And then they get a p hat of 0.6. And we try to do this as many times as I can, depending on the time that we have. But to really help build your intuition, you want to kind of visualize or kind of go through this process in your head. And I would do this, get all the different values, and then we plot these values on a dot plot, and that's going to create a distribution. So here's a dot plot that I got from the last time I did this with my students. So I did it with 35 groups. I think some groups of students went twice, and they took samples where they only picked 20 chips, and here we plotted all the 35 proportions that they got. And then we calculated, what the mean was and the standard deviation. And we actually found the mean was pretty much 0.5. And we could argue that it's getting close to symmetric. We calculated the standard deviation was 0.112. Now, here's the thing, how many possible, combinations of 20 chips can you make from this, population of 200? And the answer is that there's a lot. If you were to calculate it, it would be 1.6 times 10 to the 27th, very large number. So it's not realistic to go through all this. Obviously you're not going to have time to do this. You're going to need some technology to actually see what would happen. So let's look to see how we, get a sense for what would really happen in the real world. All right, so technically, the sampling distribution of our statistic p hat, the proportion of red chips that students would get from samples of size 20, that would basically be the distribution of all those possible combinations. Now, as we kind of I just said, and as you can understand, it's pretty much impossible to kind of do this in real life. So instead, we use a simulation to kind of see what would happen. So down here, here's a simulation where they did this with 500 simple random samples of size 20. Still, 50% of them were red, and this is what they got. And so what's going on here, let's look at some of these questions. We have a dotted 0.5 or 0.15 is over here. And what that means is that in one of those samples, 15% of the chips were red, so 3 of them, 3 out of the 20 chips. So there's one group that got 3 out of their 20 chips that are red. The shape, you can start to see it's starting to look pretty symmetric, centered at 0.5. The values are going from 0.15 to 0.8, and we could maybe say that's an outlier. Now based on this, if we were to get a sample proportion of 0.85, let's say if I was to get one of my groups of students to get 0.85 in their sample of 20, would that be pretty rare? Would that be surprising? And we could say, yeah, because from this, they took 500 of them and they didn't even get 0.85 once. So we can argue that it's pretty rare. We wouldn't say that it's not necessarily impossible, because we did get a 0.15, and 0.15, is 0.15 away from 0, and this is 0.15 away from 1. We could probably argue that they would occur about the same amount of time. All right, so the next question we need to ask is, well, are these statistics that we're going to get from these samples, are they going to be useful? Are they going to be reliable? So let's talk about that now. So we have to basically understand this idea of what's called an unbiased estimator versus a biased estimator. So we say an unbiased estimator is a statistic we say that a statistic is, an unbiased estimator when it starts to, be centered at the true value of the mean of the sampling distribution. So for example, we were getting those sample p hats, they were going back and forth, above 0.5 to below 0.5. but they eventually, we could see that they centered at 0.5. We could go back here. They varied, but it was pretty much centering right at true proportion. So we could say that the sample proportion p hat is an unbiased estimator. Well, let's explore this a little more so we can really get a conceptual understanding. So another activity that I would do is I would have these index cards. I usually have about 200 of them, and each index card is a number. And then I have my students are going to draw a certain number of index cards. Usually I'll say 5. So they'll draw, 5 index cards out of the 200. Now, there's I'm not going to reveal what the numbers are yet, but let's say they get like on one of the index cards, they get a 50, they get a 51, you get another one, they get like a 60, and they get like a 49, and they get like another 51 or something. So from here, they're going to then calculate what their sample mean would be, what their sample range would be, and what their sample median and standard deviation would be. So let's look at like a past activity I did, so we can see so we get a better understanding of what's going on. All right, so here's a table with past data that I did previously in one of my stats classes. So this sample, so the fourth sample they drew, they got these 5 numbers, and the mean of these 5 numbers were 48.4. The range were 7, 47 to 54, 7. The median, the middle, is 47, and they got a standard deviation 3.07. And so we did this, or my students, did this for a total of 30 different samples. And these are all the values we got. Now, what do we do with these values? Like what's going on? Well, if we want to figure out what the true mean is, this is going to sound kind of weird, but we actually take the mean of the sample means. So you're like taking the mean of the means. So we take all these values, add them up and divide by 30, and we will get 50.06. So the mean of the means, if you want to think about it like that, was 50.06. So we would do this same thing for all the other statistics. So we found all these ranges. We're trying to find what was the mean range that we got from those 30 samples, added them all up, divided by 30. We got a mean range of 9.3. Same thing for the median, and same thing for standard deviation. So it's the mean of the samples. Now let's keep in mind the samples have to be of size 5. So here's the data. Now, so the question is like, are these values, are these good estimators of what the true means of the population? So is this a good estimator of the true population mean? Is this a good estimator of the true population range? Is this a good estimator of the true population median? And is this a good estimator of the true population standard deviation? So are these pretty close? Are these like centered at those values? So let's see what actually happens. All right, so what we do next is then we look at a dot plot of the sample means, and then the dot plot of sample ranges, and dot plot of sample median, and a dot plot of the sample standard deviations. Now, again, these values don't represent the card values they got. So like, let me flash back to the data. They're not representing these values. These values represent these 30 values. We put all the means on just one dot plot, and that's what we got here. We rounded them to the nearest 0.5 to make it easier to graph. And what we see is that I tell them after, well, true population mean was 50. And what they got from the mean of these 30 samples was pretty much about 50.06. So like, it'd be somewhere like pretty much spot on if we were to say like, that's the true mean. And that goes with the population mean. So this would be an unbiased estimator because it's pretty much centered right at the true population mean of 50. Now let's look at the range. So these are the 30 values that represent the ranges of those 30 samples of 5, numbers that they got. So again, it's not going to be these values, it's the ranges they got. And so we plotted these, and this is going to be something, interesting. And this is what you want to understand. The true population range is 20. So the true population range is somewhere around here. That line will be the population range. But the mean of the 30 samples ranges, those mean of those 30 sample ranges that we only got about 9.3. So like somewhere over here. So we are way off. So it's pretty off. So we call this a biased estimator. It's biased. It seems to consistently, or seems to be pretty much always estimating the true population range. And this makes sense because let's think about this logically. The only way you would actually get the true population range from a set of 5 cards is if your set of 5 cards had the highest value in the population and had the lowest value in the population. And we probably understand that's going to be rare. It has to have both. Any other two wouldn't give you the true population range, and it would have to be lower. So the population range is always going to be above what we would get from these 30 sample ranges when we take the mean of them. So again, that would be a biased estimator. Now let's look at the dot plot for the sample medians. So again, it's the data from these 30 values that we got from calculating the medians of the 5 numbers that the students got. And when we took the mean of these 30 sample medians, we got it right about 50, which is right on the true population median. So this is a good estimator. This is unbiased. And lastly, standard deviations. The sample standard deviations that we got are plotted here. From the 30 samples, we got a mean standard deviation about 3.5. So somewhere around here. And that would actually be biased. It would actually, again, be below the true population standard deviation. It should right below 3.97. So again, this would be a biased estimator. So in general, sample standard deviations are not good to estimate, the population standard deviation, and same thing with the ranges. Standard deviations are biased estimators, but it looks like medians and means are, unbiased. Looks like that we can trust them. All right, so that's one factor we want to consider. We definitely want an unbiased estimator. Now, another factor we got to consider is something that deals with the precision of our samples, like how precise our sample is going to be. So let's look at this example. So this might have been before your time. There's this show that was called Survivor. I never actually watched it, but I heard it was good. Anyways, so they were trying to figure out what the true proportion of US adults who watched Survivor was. So let's say the true proportion was 0.37. So here are two different sampling distributions that they use to, to kind of estimate this. Now, on top here, they took samples of size 100. They took 400 total samples of size 100, but in the bottom, they took 400 samples of size 1000. So the same number of samples were taken, but the number of individuals in each sample was different. This had, again, each sample with 100 individuals, and this one had each sample with 1,000. And you can see they're both pretty much centered at the true population proportion, 0.37. However, this is what we call more precise because there's less variability. It doesn't vary as much from the true proportion as this one does. And as you can understand, that's what we like. We want to have good precision, good accuracy when we're taking samples. So that's going to be another factor that we want to consider when we're doing statistics. All right, so to sum up, larger random samples give you more precise estimates than smaller random samples. And to put it simply, it's because they just give us more information. You know more about the population with a bigger sample. So let's think about this now, kind of like we're going to do like an analogy. But before that, let's make sure we understand that just because you have a large sample, it's not going to take care of issues like bias. So make sure that you still conduct your study appropriately. Make sure you use the correct random sampling methods. Because if you were to do something, a voluntary response sample, just because you have a big voluntary response sample doesn't mean that data is going to be useful. The sample we could say is worthless because of bias. All right, variability of a statistic. Here's the formal definition. I like writing, definitions because I guess it helps me retain it better. But let's look at this in terms of like we're firing an arrow at a target. So maybe shooting a bullseye. So there's a couple of different things that happen. Let's say we'll have 4 general cases. So one case is, again, we're trying to aim for the center, but we keep on, we keep on shooting over here. We keep like our shots vary and they go over here. So it's as if the center, if the center was over here, we'd probably be pretty close, but it's not. So what we have here is that we're biased in this direction. We say we have a high bias. High bias, and maybe to the top right. Maybe if you play sports, if you shoot a basketball, maybe your shot is usually long, or maybe if you play soccer, or kick it or something, maybe you're biased, in that sense. That's one way to think about it. But we have low variability. We don't really vary much from this area. So we say high bias, low variability. Now let's take another case. Maybe we were, our shots would go like this. We'd be up, there, maybe one over there. So they're all, kind of like around the middle. So we're not really biased. We're not really biased in any particular direction. We have low bias. We're not, consistently shooting up or below or left or right. But this means because we have high variability. Again, because our shots are varying in all different directions. Now, we could also, maybe be something like this. If we're shooting there, that, there. Now, this is probably the worst case, I would say, because you're biased in this direction, but you're not even really consistent. You're like all over the place, even in that direction. If the target was here, sometimes you shoot above, sometimes you shoot to the right, left. So you have high bias, you have high variability. And that's what you don't want, or that's the last thing you want. What you ultimately want, as you probably understand, is you want low bias and low variability. You want to basically be shooting all the time near the center. So that's the ultimate goal. Low bias, low bias, low variability. Variability. So this is our goal. You know, maybe it's sports, but also in statistics, we want to conduct studies and perform statistics so we have low bias and low variability in our data. All right, so that's a good introduction for sampling distributions. And I'll see you in the next video where I'm going to go into more detail on sample proportions.